Good day, everybody. So today let's take a look at certain topics from our organic chemistry explorations. And today specifically, we are going to focus on alkenes and alkynes, just some foundations. So what we're going to do is just get into practice right away. And by that, I mean drawing various structures, right? So for example, let's just start with them simple foundational thought. Okay, what is an alkene, right? So yeah, here I think it's going to be a good idea to just show some example of what an alkene is, and then we're going to make a chain. Let's make sure that there is enough carbons, such as maybe 7 carbons, for example. 7 carbons, right? It will be like here. So that looks like the beginning of the skeletal drawing. So, but we also need to be able to go between skeletal and expanded conformations or drawings quite easily, right? So at this point, I'm going just to show the skeletal or line I mean line angle structure. So because it consists literally of lines and angles. And then here we have 1, 2, 3, 4, 5, 6, 7, right? So 7 carbons total. So then right now we have an alkane. By the way, if you think about the names, right? So just try to scaffold your knowledge here and skills. Okay, so I can draw, for example, the skeletal drawing of some kind of like organic compound, right? So now can I name it, for example? It's going to be kind of potentially the next question. Right, so here in this case, it's just a straight chain alkane as we see it right now. So it contains 7 carbons, and consequently, this will be a heptane, right? So pay attention to the suffix here, it is ane, A-N-E, heptane. So, but if we have a double bond, so maybe between carbons 1 and 2 here, so at this point we already have the alkene, right? So it is an alkene. If you want to name it, so we can do that. So remember, how we can potentially name or number rather the longest chain, right? So that's what we need to also find out in alkenes. Just find the longest chain first, right? So like what is the longest chain? So yeah, maybe you will have a chain of 7 carbons and then no other chains. Okay, that's good. So the choice is pretty straightforward, right? So that's going to be your longest and only chain. So but what if you have something like that? Maybe you have here, let's say, something like this, right? So let's say you have an ethyl in your substituents, right? So that potentially can be in an alkene. Like nobody said that the alkenes must be always like straight chain compounds, right? No, they can also be substituted. And as a matter of fact, some natural products are alkenes, or they contain the alkene functional group, and they can have like very complicated structures, right? So which are kind of basically full of various functional groups, maybe multiple double bonds, right? So it can become really complicated if you think about the sheer variety of organic compounds and ways to like position double bond in like some kind of organic molecule, right? So, but anyway, so right now we have here potentially several chains, right? So yeah, this one, okay, is identified to be the chain with 7 carbons. What about this one? 1, 2, 3, 4, 5. 5 carbons, pretty long, but not the longest, right? So, although it also has the both the two carbons that contain the double bond, right? So that's what we also, as we recall from the rules earlier that we saw, we need to be on the lookout for the chain, the longest chain that contains also both carbons that make the double carbon double bond, right? So this is kind of like not the longest chain because it only has 1, 2, 3, 4, 5 carbons, right? So this is going to be our longest chain so far. So if we take a look at this chain, 1, 2, 3, 4, 5, 6, 7, it also has 7 carbons, but it does not entail the carbon-carbon double bond whatsoever, this chain which I'm trying to trace like that, right? So consequently, you are going to choose this one. So that's your longest chain. Okay, great. So now we're going to number it. So do we number from this end or from that end, right? So that's the question. So to answer that, we need to like again recall some rules. So which one of them will be saying, okay, well, we need to number from the end that is closest to the commencement of the double bond, right? So this end is pretty far from the commencement of the double bond, which would commence on this carbon if we try to number the chain from right to left. If we number the chain, the longest chain from left to right, so then we will have a much faster, earlier commencement of the double bond on carbon number 1 already. Okay, let's make it so. 1, 2, 3, 4, 5, 6, 7. Okay, great. So then my next thing will be to circle the groups, right? You're welcome to use the colors as we always say. So, but for now, I'll just use the black ink everywhere. So here we have, that's our ethyl technically, right? So we have the alkyl substituents. That's kind of like another review of the terms that we have seen so far, right? So then what's next? So next we are going to put together the name, right? So because we have all the building blocks here. Okay, so what about them? So here we go. We have 7 carbons in the chain, right? So the root will be kind of like similar to the roots that we saw in alkanes. For example, 7-membered alkane chain, just a straight one, will be having the name heptane, right? So heptane, and which can be substituted, but the parent chain name will be heptane. So if we have an alkene, so heptane switches to heptene, right? So we are going to have heptene as part of the name because we also need to entail or account for the substituents and the double bond position, right? So, but overall, we are going to have heptene. So that's already part of the name. Heptene, because we have the 7-membered chain with a double bond. So it is an alkene consisting of 7 carbons in the main chain. So this will be hept. So that's the root saying that we have 7 carbons, right? In for alkene, right? So pretty logical. So now we're going to show the position of the double bond. We need to show the carbon, number of the carbon where a double bond starts, and then it will finish at carbon n+1. So starts on carbon number n and finishes on carbon n+1, right? So here we have 1, 2. So finishes on 1. I mean, starts on 1, finishes on 2. It cannot finish on like 6, right? So that will be not the case. So then in this case, you are going to have the commencement of the double bond on carbon number 1. Okay, it's going to be 1 heptene. Finally, we are going to show the carbon to which the substituent, so far we have only one here, it's going to be ethyl. We're going to show the carbon to which the ethyl is attached, and we are going to say that ethyl is there, right? So on carbon number 3, we will have ethyl, so, or an ethyl group. So 3-ethyl. 3-ethyl, 1-heptene. So that's going to be the name of our alkene, right? So just real quick, so if we have an alkyne, so we'll have a slightly different situation, but the naming will be very similar, right? So that's why I'm trying to like make this segue into alkynes right away. So before drawing the expanded structure, which we're going to take a look later. So there is also going to be like a special feature when we draw the alkynes. So as we remember, the alkyne, by the way, so like speaking of like scaffolding and building blocks of your knowledge, you can also like ask yourself, like, what about hybridization, right? So it's kind of like, I'm just giving you some kind of ideas which you can potentially like sift through in your mind. So, and here one of them is a hybridization, right? So that's the term. So at this point, you can maybe like pause the video and recall kinds of hybridization, right? So just pause and recall. So, but now after you unpause, we are going to take a look at the hybridization kinds in this molecule, for example, right? So right now, let's take a look at the alkynes. So for alkyne, we need to have just a little bit of the modification. There's going to be no band because alkyne carbons, the ones that participate in the carbon-carbon triple bond formation, are known to be sp hybridized, and their geometry is linear. Consequently, we cannot have the band, right? Which can be had in case of alkene, because alkene double bonded carbons possess sp2 hybridization, and they are geometry-wise trigonal planar. So that looks like a triangle here, right? So at least partially. So now let's kind of like erase this situation, and then if we want to show the this carbon, if we assume that it participates in the triple bond, so what we're going to do is we're going to show the straight geometry for this carbon. How? So I'll show you how. So that's going to be done in the following way. So that's going to be the carbon-carbon triple bond, so which now consists of the sigma bond, pi bond, and another pi bond, right? So now it's proper, and now that's going to be enough. Maybe this bond will be a little bit longer. So yeah, but yeah, that's it. Sometimes they're all like equal and then finish at the same point. So maybe it's going to be better to show that they finish kind of at the same point. So they finish here, right? So that's what you would officially see in official drawings in like chemistry software, for example, right? So here we need to realize that we have an and here, right? So then and then this end is a carbon, right? So this carbon is bound to another carbon that has the also like triple bond, right? So it's a two carbons which are triple bonded. Where is that other carbon? So is it here? No, it's too far. So this is honestly SCH carbon, if you think about it, right? So that cannot be like a triple bonded carbon. Otherwise, this carbon would have one, two, 3, 4, 5. So that's too many bonds, right? So basically, the second sp hybridized carbon that participates in the triple, in the carbon-carbon triple bond formation is found at the end of the triple bond, basically here. So that's the end. That's where it finishes, right? So that's the finish line, and that's your other carbon. So that's it. That's what you will see in all other kind of like drawings of alkynes in skeletal formulas, right? So then that's it. So that's going to be your alkyne. You see, it's almost like the same looking thing as an alkene that we drew previously, but there is a difference, right? We want to show the straightness of the geometry, the linear geometry of the carbons in the following fashion, right? So this kind of like straight line is drawn in line with the single bond that connects this sp hybridized carbon to the sp3 hybridized carbon in this kind of like alkyl part of the molecule, right? So anyway, so if you want to number the chain, we are going to start numbering with the end closest to where the bond commences. Here it's going to be number 1, then carbon number 2, 3, 4, 5, until 7, and so on, right? So then here, so the carbon where the triple bond starts will have a smaller number, right? If we number the chain from left to right, as opposed to right to left, right? So, okay, so we minimize the number for the carbon at which the triple bond starts. So then we have the substituents. It's going to be also, the longest chain will be also 1, 2, 3, 4, 5, not the longest. So 1, 2, 3, 4, and then 7, that's the longest chain, right? So it's the same longest chain. So we also have the substituents, so it's going to be ethyl. So if we have the 7 carbons in the main chain, then we will use the root hept, right? That kind of like has the name from the word for 7 from the Greek language. And then we're going to modify our, what's it called, suffix, right? We're going to modify our suffix. So it's not going to be heptane, not heptene, but heptine, right? So because wine, Y-N-E, is the suffix that kind of like shows that you have an alkyne as your molecule which you are trying to name, right? So 3-ethyl, so this ethyl group here, 1 heptine on carbon number 1. On carbon number 1, the triple bond starts and finishes on carbon number 2. It cannot potentially go to carbon number 4 all of a sudden, right? So that's like basically what we have. So it's carbon I, and then it finishes on carbon I plus 1, right? So that's your like general like numbering thing that you can see in other sciences. So anyway, so that's going to be our alkyne situation. So now maybe let's try to draw some like more structures, right? Such as expanded structures. So we can do that. So here we go. So I'll just remember what the structure looks like, and let's make it into the alkene first, right? So if I want to draw this seven-membered alkene chain, so it's going to be looking like that in the expanded fashion, right? So C double bond. So that's not the best double bond, so let's make it more proper, like this. That's my four carbons, three more. Okay, so then I'm going to show the CH bonds, just like this. So notice how I draw them, right? So I'm just trying to form like a tetrahedral shaped things, or carbons rather, right? So when I am drawing the like alkyl chain or like alkane part. All right, so now we approach this one, right? So that's a tricky one. So it's a new pattern. Double bond, single bond. So we have only one more bond left. So don't draw like two bonds here. So it's going to be one, two, three, four. Four bonds, right? So what don't we show? We don't show carbons and hydrogens explicitly, right? So carbons are, as we remember, in bands and termini of our drawings. All right. So, but here we are going to, like we already show the carbon. So consequently, we're going to show something that is missing. What's missing? It's the hydrogen, right? So we can also have the hydrogen here. So maybe one, maybe two. So right now we need to decide, okay, three bonds are occupied already out of four. So consequently, we can only attach one more hydrogen. So in this case, however, if you look at this carbon, it only has two bonds engaged, right? Into the bonding with another carbon. So consequently, we have two more bonds available, right? And you see here I'm showing this like trigonal geometry. So the positioning of these bonds, single, double, single, looks like a triangle. A double, single, single, triangle again, right? So I on the termini I have the carbons, right? So then I show that and I'm going to beef it up with the respective number of hydrogens, right? So here what I don't see is kind of like after I identify the carbons, I don't see hydrogens, right? Explicitly, but I can show them in the expanded formula. So that's what the expanded formula is for, to show everything that you have atom-wise and bond-wise in your particular molecule. So let's add two more hydrogens will be possible to add, and that's it. So that's what we have by default, right? So like if we translate our skeletal drawing into the expanded structure. So on carbon number three, we also like have ethyl. Let's show it, right? But of course, we need to sacrifice one of the uh, H's, right? So to make the bond to the ethyl group. Maybe like this. So that's our ethyl, CH3, and the CH2 will be present. Okay, great. So that's our ethyl. Great. So yeah, we now have the expanded structure, right? So if we want to switch alkene to alkyne, no problem, we can do that. So, and the expanded structures will be almost the same, right? Except we're going to show the alkene expanded like drawing. Let's do that. So remember, so the triple bond has to be kind of like linear, right? And kind of like the triple bonded carbon, it will be in line with this bond, right? So between the triple bonded carbon, sp carbon, and then sp3 hybridized carbon right here. So that's what it will look like if we want to show the alkene. So it will not point down, right? So there's going to be not like 120-degree angle, but rather 180-degree angle between the triple bond and the single bond right here. So then if we have the alkynes, so we should also not forget about the other carbon because, well, we're showing the expanded structure, right? So like we need to show all the atoms anyway and bonds. So we definitely shouldn't forget about this carbon. So triple bond, so that's what it looks like. Okay, so if you look at each carbon, this carbon already has three bonds and four used, right? So you cannot attach any more like hydrogens here, right? So they just are not shown, and then they cannot be there, right? So the terminal carbon has 3 bonds out of 4 used, right? So what's not shown, in addition to carbons, is hydrogens in skeletal drawings. So we identified our carbon on the terminus here. So then we also identified that this carbon only has 3 bonds attached, engaged so far, right, into the bonding. So 1 bond is empty. And then it must not be empty, so it must be occupied with what? With an H, which is also implied in the structure, right? So that's what the terminal alkyne will look like, right? So that's your alkyne expanded drawing. Enjoy. So what else can we have, right? So let's maybe kind of like think about some sort of like look into the future, because we will be inevitably building up on this like fundamental knowledge, right? So which, if you notice, is just not about even reactions yet, right? So we'll get to the reactions as soon as we can. So, and what we're gonna do is, before we get into the reactions, we'll be like, okay, well, what reacts, right, exactly in organic compounds, right? So it depends on the structure. So as you might see, or you already did see some reactions even in our like exam, right, which preceded this session. We were looking at various functional groups, right? Functional groups, that's what kind of like reacts in a myriad of ways in organic chemistry. So for example, if you recall the carboxylic acid functional group, so this one can react, right? So for example, we at this point should be able to handle the dissociation of the carboxylic acid functional group, because it is kind of like, to a large extent, knowledge from it's a piece of knowledge from the general chemistry courses, right? So, and this is going to be the reaction of the functional group, right? So just dissociation of the carboxylic acid, right? Or maybe the acid plus base, right? You can also have carboxylic acid plus inorganic base, such as potassium hydroxide, right? So again, try to recall what potassium hydroxide is, right? So because it is like a very common compound, no matter what chemistry you look at. General, inorganic, organic, medicinal, right? So it's going to be like, or synthetic. So it will be encountered there like to some extent, right? So that's why it's a good idea not to forget your like background and prerequisite knowledge, right? So that's why you have prereqs for courses. But I digress. So let's take a look at the stuff, right? So for example, we have some kind of like a alkene. Let's show an alkene, for example, that looks like this, right? So we have an alkene of some sort. We are going to have maybe some sort of group here, right? Such as CH3, right? So I'll just make it fundamental. So, and here you go, right? So what's happening here? So it looks like the reactions a lot of times in alkenes will be taking place at the location of the carbon-carbon double bond, right? So that's what was determined about alkenes. And then basically, what do you remember, right? So like what happens in reactions? Like double bonds, not double bonds, but some bonds are broken and some bonds are made. So it looks like, turns out that this bond, as we remember, consists of the sigma and pi bonds. So these are all sigma bonds. And then in CH3 groups, we also have sigma bonds, right? So experimentally, it was found that sigma bonds are stronger than pi bonds. And then pi bonds are weaker than sigma bonds. What does it mean? So if you have a weak bond, it has a more tendency to be broken and consequently participate in reactions, right? So that's why, so we have like specifically good reactivity at the carbon-carbon double bond. Why? Because it has a weaker bond pi than the sigma bond, and then this bond can be broken and new things can be, for example, attached to these sp2 previously hybridized carbons, right? So, and then potentially, if you think about that, you can go from the unsaturated compound to the saturated compound, right? So, basically, in saturated alkanes, right? It's kind of redundancy to say that alkanes are saturated compounds. They don't have any double bonds, so they are all engaged into bonding with other atoms, right? So there are no carbon-carbon double bonds in saturated compounds. So there are only single bonds. So then what happens next is that we are going to break the pi bond, for example, right? And then let's imagine we are going to break the pi bond. So then we will attach H to this carbon and H to that carbon, right? So because each hydrogen, if you imagine that, comes in with an electron, right? So, and now if you break the pi bond, you don't have the pi bond between two carbons anymore, right? So now you have the free electron and free electron, which are disconnected. And now they will connect with electron from the H, and this electron will connect with this electron from the H. And then if you visualize it, maybe you can draw it on a piece of paper as another challenge. Maybe you can visualize it in your brain. So you will be able to get an alkane, right? So you'll get the saturated compound. So yeah, basically, those double bonds will turn into single bonds, and then the bonding amongst atoms will be maximized, right? So, because if you think about that, so this compound, right, alkene by itself has a particular number of carbons. So how many? 6 carbons, and it has 3 by 4 hydrogens, right? 3 by 4, 12. C6H12, right? So, but if we break the pi bond, we are going to add more hydrogens, right? We'll still have the same number of carbons, C6, but the hydrogen count will be 3 by 4, 12 plus 2, 14, right? So we saturate this compound with hydrogens, right? So that's why we go from the unsaturated to saturated, right? So basically unsaturated compounds can get more atoms, right, with which they will be saturated and turn into saturated compounds. So that's the difference between this kind of like unsaturation and saturation. Saturation, you basically cannot like add more stuff, right? Maybe you can chop something out and substitute it with something, but it's not the addition, it's substitution, right? So, but in case of unsaturated compound, you can start with, okay, some like CX HY, and then you can go from that to CX HY plus 2, for example, right? You can add extra atoms. You don't have to kind of remove something to switch it to something else, right? But you just need to add, right? So that's the addition process. So those terms, actually substitution and addition, coincidentally, are used a lot later on to describe various organic chemistry reactions, right? As a matter of fact, those are some of the major types of organic chemistry reactions, addition and substitution, right? So we'll be looking at more examples later as we explore our functional groups, right? So same with alkynes. So alkynes, if you think about it, so again, a little bit of the review, right? So let's take a look at some like random alkyne. Oh, no, that's a bad drawing. So, which is going to be looking like this. Maybe CH2 and CH3. And then here, maybe we'll have carbon with, I don't know, methyl and another methyl, right? So these alkynes, so as we remember, so it has the triple bond, right? So now we're going to remember more stuff, right? What is a triple bond? It consists of one sigma pi, so that's the pi bond right here in the middle, and another pi bond, right? Sigma pi pi. So as you see, it has like two weak bonds, right? Two pi bonds. They can also be broken. So if you imagine the electrons here, 1, 2, 1, 2, right? So now potentially, if you just use the same logic, break the pi bonds, and then use the liberated electrons to bind with other electrons of other atoms, right? So potentially you can saturate this unsaturated alkene compound, or alkyne, sorry, with 4 hydrogen atoms, right? So that's how you saturate it, and eventually you can make it into an alkane, right? It becomes like simpler, just single bonds only. So it's saturated completely with like potential like atoms that can be added, right? Such as like H's. Maybe it's going to be chlorines, right? So you can also do that. So there's going to be like, as we can like predict at least, right? Or imagine there could be like a myriad of things that you can like add. Not everything, of course. So there are some kind of constraints, right? At which we'll be looking. That's why we will have like particular reaction types, right? In which, for example, we can add, let's say, hydrogen atoms to the unsaturated molecule, right? Such as like alkene or alkyne for now. So maybe we can add halogens, right? Maybe we can add like HCl, hydra halogens, right? So, or HF, HBr, things like that. But maybe we cannot add this some sort of like any compound, right? So that we imagine so, but it's going to be kind of like, again, a set of compounds, a pretty good like set that we can potentially add, right? So to those unsaturated compounds to make them a little bit more saturated with atoms and like function groups, substituents and whatnot, right? So yeah, so here basically we can have one bond, another bond, so it is two CH bonds, and then the third CH bond and the fourth CH bond. Four extra total CH bonds might be formed, right? And then as you see, so if you redraw that into the respective alkane by virtue of breaking those bonds and making the CH bonds using those electrons and these electrons here on H's, then you'll be able to make the alkane. So then you will switch from your alkyne unsaturated to alkane saturated molecule, right? So that's going to be kind of a little bit of the flavor for the future for you. And for now, just kind of like look at those things. They're like pretty fundamental. That's not a lot of information, hopefully, but at the same time, it will be important to master it now because it will be used later. So, and at this point, I thank you for your attention and have a good day. Bye, everyone.